Okay, welcome to our webcast. I'm Lester Knutsen with Advanced Data Tools, and today we're going to talk about database indexes and best practices for Informix DBAs. And I was working on updating my Informix DBA class and updating the sessions. And I sort of, as I was working on the one on indexes, I said, that would make a good webcast. And so decided to do this one today to talk about indexes. I'm not going to go full screen because I can't see the chat. Well, I will a few times, but when I go full screen, I can't see the chat and I can't see the participant list. I am going to go full screen for a few minutes and then I'll come back so I can see everything else. I'm Lester Knutsen. I've been working with Informix since 1983, back when Informix was just getting started. And it's been a great product to work with over the years. It's been a blast. One of the reasons I started working with Informix was because of indexes. I was originally a C programmer, and I really liked the C ISAM libraries that I could get, which allowed me to build indexes out of flat files. Now, this webcast is being recorded, and if everything works, we'll have a replay up in a few days. Also, I'd like to ask everyone to mute your line. Any background noise will be distractions. Now, there is a chat button, though, and feel free to put questions into the chat at any time. I may not answer them right away, but at the end, if we have time, I will go through the chat and answer as many as we can. So we're going to talk about indexes and how they can improve your performance. We'll talk a little bit about the cost of an index, what happens if you have too many indexes and how that can slow you down. We'll talk about locks and monitoring indexes and all kinds of new stuff in this presentation today. But I want to start off. This was a bit of a quote I found at Wikipedia about indexes that I thought was very good. So indexes are structures that improve the speed of database retrieval on a table. Indexes cost additional writes, that means additional I/O, and additional storage. And so there is a cost to indexes. Wikipedia also says that indexes are used to very quickly locate a row. And here's an example I wanted to start off with, and just a simple demo of the performance improvements of an index and no index. I'm going to run the same SQL, and I'm actually not going to run it. I'm going to show you it ran. It took 9 minutes to run without indexes. And in that 9 minutes, it scanned 8 billion rows. And the SQL estimated cost was $1.3 million. So that's quite a bit of SQL cost for that. So let me just show you the SQL. That's the dropping the index. So this is sort of what it looks like. It's a very simple update, a table, and I select something from another table based on a field called zip, and there has to be, if there's no index on zip on either table, it's going to do a sequential scan of that table. And so let's just quickly create the indexes. I'm going to come in, pick create the indexes. That creates the indexes. And now I'm going to run the script. And you see it's flying now. This took 2 seconds 2.4 seconds. And that's the power of indexes. If you have the right indexes, they can be quite a bit faster. Also, it had less I/O, and the SQL cost was quite a bit less. Now, Informix has 4 kinds of indexes, and the B trees are the most common. There's another kind called forest of tree indexes, which is a B tree index, a special case of it with multiple nodes. There's an R tree index that's used for spatial and 2 or 3-dimensional data. And then there are functional indexes. Functional indexes are indexes that you create, or you create a function that then is used by an index. And I'll show you a simple example of that later on. Now, let's compare an index to a sequential scan. Data rows are stored in a table. They're stored randomly. Sometimes they're stored by how they're loaded, but if you've deleted a bunch of rows and you load some more rows, they may go in and fill up the deleted slots. So your data could be random. A sequential scan has to read from the first row to the last row. It can't stop halfway through unless you kill the transaction. So it reads the rows in random order. And there are times when a sequential scan is faster than an index, particularly when you're reading a lot of data, like if you do a select star from a table with no where clause, a sequential scan is the fastest way to read that data. But otherwise, having the right indexes can make reading that data quite a bit faster. So let's take a look at what a B-tree index is. A B-tree index is like the index in the back of a book. I'm looking up a term in the back of the book. I go to the letter of the alphabet that term is. Think of the letter of the alphabet as the root page. And then I scroll down through the entries on that page, and I find the entry I'm looking for, and it will tell me the page number that entry is on. And that's exactly what an index does. Let's say you have an index here on dates, and the root page will say, okay, if you're looking for dates in this range, let's say from January to February, go to this branch page. If you're looking for dates in February to March, go to this branch page, and so on. There may be other branch pages here. And you get to a branch page, and it may tell you that, okay, if you're looking for January, go to the leftmost branch page. If you're looking for February, go to the rightmost branch page. And then the branch page will send you eventually to a leaf page. And a leaf page is the bottom of an index, and it has the address of that row on disk. So it will say, okay, you're looking for this date, and the address of that row on disk is this. So to read an index, it does take a few reads. You have to read the root page, you have to read the branch page, and then you have to read the leaf page before you get to a row. And on average, if you have 3 levels like this, it'll take you 4 or 5 reads to get to a row. So this is a bit more description of that. How do you estimate the size of an index? There's a very good description of that in the Informix IBM manuals, and I have a link to that for 12 here. But the basic formula is it's the size of the column plus 4 bytes times a unique percent. And the unique percent is a point. Like if it's half the rows are duplicate, it'd be 0.5. If most of the rows are duplicate, it might be 0.10 to say that there only 10% of the data is unique. And then you add a row pointer, which is the address of that row on disk. And this is going to be 5 bytes for a non-partition table and 9 bytes for a partition table. and then you multiply that by the number of rows. Now, this is not going to be precise because indexes grow and shrink, and they live on pages, and there may be empty spaces in the index as you add and delete pages. But this will give you a ballpark for how big an index will be. The big thing is the column size. The more columns you index, the bigger the index is going to be. If you index a 50-character column, that's a lot. And so you want to look at indexing smaller columns. The smaller size, the better. This is also why you don't want to index every column in a table. Now, you can create an index, drop an index, and in 12, everything I'm going to tell you except for one slide will work in 12. One slide is what's new in 14, Informix version 14. And some of these will work in 11 and earlier versions. But in 12, you can say create index if not exist, and it will create that index. If it already exists, then it knows it doesn't need to create it. And you can drop an index and say drop index if it exists, and that will drop that index. So it's very simple syntax to create an index. You give it an index name, you tell it the table, and you tell it the columns to make an index of. Now, in version 11, the later versions of 11 and 12, they added the keyword online. And this allows you to create an index while the engine is online and up and running. Now, what it does is it doesn't lock the table. To create an index without the keyword online, it has to lock the table because it can't have people changing data while it's creating the index. Creating an index online means the index will not go into effect until it's all completely done. It sort of runs in the background. If there's an existing index, it won't be dropped, so people can be using the existing index. And then once it's done, it will mark that index as available for use. It will update it to the latest rows and then make it available for use. So it's a cool new feature. It is slower when you do it online because it can't just go out there and create the index super fast. Now, I was going to talk a demo about scans versus indexes. I'm going to talk about that because my demo ended up taking too long. When is a index or a scan better? And the example I want to use is a table with 100,000 rows and 4 index levels. That means if you're going to read the table with a sequential scan, there'll be 100,000 read operations, 1 per row. And no matter if you're only looking for 1 row, a sequential scan will read all 100,000 rows. An index with 4 levels for each level and 1 read for the row will take 5 reads. So you can see right away, if you're looking for 1 row, an index is going to be much faster. It'll take 5 reads versus 100,000 reads. Now, this is about where the trade-off happens, and it depends on a number of things. I'm simplifying it here. So in real life, it may not quite work out this way. It depends on things like the page size, how big the index is, if the index is in memory, and things like that. If you're reading 1 row, 5 reads using an index. If you're reading 10,000 reads, it will take 50,000 reads. I'm sorry, if you're reading 10,000 rows, it will take 50,000 reads to read that table. That's still faster than a sequential scan. Now, if you're reading 20,000 rows, it may take 100,000 reads Remember, the index has 5 parts, so every row it has to go do 5 reads. This is about the point where a sequential scan may be faster. And if you're reading 50,000 rows, 50,000 times 5 reads a row is going to take 250,000 I/O operations. And this is probably the point where a scan is faster than an index. My rule of thumb, if you're going to read more than 25% of the data, a scan is going to probably be faster than an index. Again, it depends on a number of other factors. That's just a general guideline. Now, indexes have a cost. They're not free. And selecting a index has the cost of doing the reads of the different levels of that index. Inserts get really interesting. When you insert a row, it has to go insert into the indexes. And if the row has 5 indexes, then it has to go do 1 insert for the row and 5 inserts, 1 into each index. And if the space does not exist on that index page, so let me go back here to this chart here. If the page down here that it needs to insert the row is full, it has to do a split. And that can be very expensive because then it has to take this row, divide it into 2, this page, divide it into 2 pages, and rebalance between the 2 and update the branch nodes. So inserts, and this is why loads with the indexes enabled can be very expensive. Now we'll talk about fill factor in a minute. Fill factor is how much space to save when you create an index to avoid page splits. And performance on very large loads is always going to be improved by disabling indexes and rebuilding indexes after the load. Now, delete. When you delete a row, it has to go find the index entry and mark that entry as deleted. It doesn't delete the entry. It's just marked for deletion. So something else may accidentally stumble across that entry, and it will say, oh, but it's marked for deletion, so I won't use it. But the fact that it's still there and things still stumble across it and have to read it until it's actually deleted can be an additional cost. Now, in the background, there's something called the BTS scanners, and I'll talk a little bit about them later on in this presentation. And the BT scanner's job is to run through and clean up your indexes. Basically clean up deleted pages and rebalance the indexes. And this may require rewriting some of the index pages. You may end up, and this is why when you delete rows, your indexes don't shrink right away. They may not shrink until the B-tree scanner has had a chance to go through and clean them up, which may be a while later. So there is a cost of deletes. Updates have a bigger cost because basically you can't update an index entry. You have to delete the old entry and insert a new entry when you change the value of a column that's being indexed. So updates cost as much as a delete plus an insert and are probably the most expensive operations on indexes. So just keep this in mind. I've had clients that said, oh, let's just go create indexes on everything. That's never the best answer. What you want to do is have a few very good indexes that get used. And you don't want to have indexes on everything, just because that will slow everything else down. So in summary, anytime you insert a row, you've got 3 or 4 I/O operations. When you update a row, you might have 6 to 8 I/O operations. Also, if you have a log database and a transaction is rolled back, all this work must be undone. And not only is the row got to be rolled back, but all the indexes have to be rolled back. So the more indexes you have, the longer your rollback can take. So that all adds up to the cost of an index. Now, the other thing that affects indexes are locks. When you lock a row, it needs to lock the related indexes for that row to make sure no one changes them. Or if you're changing the values, you don't want someone to read bad data on those indexes. So a table with 5 indexes will typically generate 6 locks, one for each index and one for the row itself. That's why when you do large loads or updates or batch problems, you can generate easily hundreds of thousands of locks. And it has to do with not only the rows being locked, but the indexes being locked. And if the table was created with page level locking, that means the whole index page is going to be locked too, which can increase the chance of things like deadlocks. So basically indexes that are not required degrade performance. The more IO the inserts, updates, and deletes take, unnecessary locks, and the best practice is to make sure you don't have any unnecessary indexes. So let's talk about when an index is required. First of all, if you have to enforce unique columns, you need an index to do that. If you have a primary key or a foreign key, the way most databases and Informix enforce primary and foreign keys is with indexes. And you'll need an index for that. Also, indexes can improve the performance of joins. They can improve the performance of where clause queries, and they can improve the performance of sorts. If you have 5 statements in your where clause on one table, you need to look very carefully at those and say which one is going to be the best to index. And that's what you want to pick to index, not all 5, so that then it can use that to, and typically it's going to be the column that is most unique. Indexes are always helpful in joins and filters and when you do sorts, ordering by, or grouping. When Informix has to do a sort, if that column is already indexed, then it doesn't have to do a sort. It just reads the data in the order of the index. Now, when are indexes unnecessary? When the column is not used in a where clause. So if you have a column, and one example I see a lot is address. You might have city, state, zip, and where clauses will use zip, they'll use state, they'll use city. So maybe indexes on those would be good. But address, typically you're going to use city, state, or zip before you use address. And so where clauses may not be necessary there. If the columns are not used in order by for sorting, if they're not used in joins, if they're not used in primary keys or constraints, the index is unnecessary. And if you have an index, it will work. It will just add extra overhead. Now, let's talk about the different types of indexes. One that I find very interesting is the auto index. And this is one Informix creates in the background without you knowing about it. The only way you know about it is to look at the SQL explain plan, and you'll see something like this. This means the optimizer said, the best way to read this is if there was an index here. There is none. I'll create a temporary index. Now, that's a temporary index, and as soon as the SQL statement is finished, that index is gone. So it's not a permanent index, but it's something you ought to look at. And the way to find this is to look at your SQ explain plans. Here's an example straight out of an SQ explain plan. It says it's creating an auto index, and the auto index is going to be on product number in the product table. And it tells me the index is on product code. Now, system-generated indexes. Oftentimes, you'll find Informix creating permanent indexes in the background because of constraints. And when you create a constraint, if there's no index, it will create an index for that constraint. And system-generated indexes begin with a space. Here's an example. I have two indexes on this bills table. This first index is space 205-210. That is a system-generated index on bill number. And that's because that's the primary key of the bills table. And when I created the bills table and I said primary key is bill number, it had to go create that system-generated index in the background. It works just like a regular index. And one of the cool things in 14 is you can now rename these to give them more user-friendly names and do other things with them. And I'll talk about that later. The second index is an index that the user created on customer number. Now, the best practice for creating constraints, though, is to create the data table, load the data. First, create the indexes yourself. And this is very important. If you're going to create a constraint, take the time to create an index first. Then, when you alter the table to add the constraint, it will use the existing index. And so I typically say, don't put your constraints, your primary keys, in the table schema. Put them in alter table statements afterwards, and create indexes first. It will use those indexes. And then you can do things very easily, like run on checks and drop and recreate the indexes as you need it. Because the constraint will use an existing index. Now, there is a difference between a unique index and a unique constraint, and it only affects logged tables, and it only affects transactions. And the difference is, if you have a unique index for a log table, every row is checked as you go through. Now, if it's a unique constraint, it's still a unique index, but here the checking is delayed until the commit. And so you have the risk, I think, of having data go in. Let's say you have a primary key and you have a transaction, you say begin work, and you load a bunch of duplicate data. It's not going to check that on a unique constraint until you say commit work. Now, foreign keys. Foreign keys require constraints most of the time. There is a new option in 12 and 14 that allows you to create a foreign key constraint without an index. And this is very helpful when you have a very large fact table. I have a lot of data warehouses where we do this, and a very simple example is state. There are only 50 states in the US. And on a million table, fact table, having an index on state really makes no sense because you're going to get a lot of duplicates and it will create a very lopsided index. So what you want to do is create the index with the constraint with the index disabled. And here's the syntax to do that. After you've created your table, I'm saying alter table bills, add a constraint, and I'm saying the foreign key is state, referencing the state table in the state. So it looks just like a regular foreign key, and it has a constraint, and I give it a name, and then I say index disabled. Now it's still going to create that index, but that index is going to be disabled, so it will always be empty. And you'll not have the IO hit of using that index. So if you have very big fact tables, this is key. Now for this to work, you got to make sure you don't already have an index there that's enabled. There are a number of things that you have to do to make sure it will work. But basically, if you get the error message saying something's not right with this reference, that usually means there's an index out there or there's a constraint out there that's conflicting with it. But this allows you to create foreign key constraints without index. Now, they're still checked. And every time you insert a row, it's going to go check the state table because it's a foreign key. But it doesn't need the index on the build table to check the state table. It needs the index on the state table. And the state table has an index there because it's the primary key. So this all works really well. So the best practice for loading large tables with indexes. I get this question a lot. First off, you want to disable the index. You want to set the table to raw, load the data, then set the table to standard, and then enable the indexes and rebuild the indexes. When you do large loads or large deletes, it's always a good idea to drop and rebuild indexes as part of that operation, because that will make things much cleaner, especially when you're up in the 25% of your data. If you're deleting 10 to 25% of a table, it could well be worth dropping the index and rebuilding it afterwards. Now, Informix has another kind of index called clustered index, and this performs a one-time sort of the data to match the index. So it really doesn't change the index. What it does is it changes the data. It locks the table during the rebuild process, and you have to have enough free space to make a copy of the table because it does it as a transaction. And if it's a very big table, you may run into a long transaction. What I like to do is use this just for things like dimension tables that might be small, and where it's helpful to have the data in the same order of an index. And it's an alter index name to cluster is the SQL syntax to do it. Now, it can improve performance quite a bit. However, you have to do it again. And it's one of those operations where if you do this, you might want to do it like once a quarter. Because as soon as you start adding rows to the table, they are no longer in the order of the index. New rows will get added to the end of the table. Now, composite index. This is another key concept. The order of your columns in a composite index is very important. A composite index is when you have 2 or 3 or 4 columns in an index. And this is an example from a client of mine 20 years ago. I went in, they said, oh, we have terrible performance. Can you help us fix it? And I looked at their index, and the first question I asked is, okay, what do you search by? What's in your where clause? And they said, well, most of us use 4GL programs, and we search by last name and company name. And searching by last name is really slow. And I'm like, okay. That's because last name is not the first column of any of these indexes. And so it can't get used for searches. Now, when they search by company name, last name, this index could get used. But they also had company first name, last name, which when I looked at it, never got used. They had an index called first name, last name. They never searched for first name, so this index never got used. They had an index called company, which is redundant because you've already got an index up here, company, last name, first name. And then they had an index called first name, last name, which didn't get used. So I deleted 4 of their indexes, and I added an index called last name, comma, company. And now they had 2 indexes that met what was searched the most. It was always company name or last name. It was also the join. They were an interesting company. They joined things by company name instead of company ID or some code like that. And so it was used in a lot of joins. And this basically overall improved not only their searches, but their inserts, updates, and deletes, because now they had 4 less indexes to worry about. So the order of columns is very important in a composite index. Put the key fields first in building that index. Now, I'll give you another example. I wish I had a slide for this, but I'll talk about it. Let's say I worked with a government agency that did everything by fiscal year and program code. And almost every query had fiscal year and program code. They only had 10 years of data. So fiscal year contained a lot of duplicated data in their big tables. Program code, they had 70,000 program codes. When you have something like that, putting program code first and fiscal year second makes the most sense, because you want the field, if they're both going to be used, that's more unique first. Now, in their case, though, they partitioned the data by fiscal year. So then it made sense to have fiscal year be the first field, because that made each data a partition. So if you don't partition the data, have the most unique field first. Something else to consider in indexes is index fill factor. Now, I know I'm throwing a lot of information at you guys very quickly. Fill factor is how much do I fill up an index page when I create an index. The default is 90%. And what that means is Informix has a page and it will fill up 90% of that page and then start a new page and save 10% for new inserts in the future, so it doesn't have to split an index page. Now, that's great. You waste 10% of the space when you first create an index, which is good if it will save splits in the future. But sometimes you have index pages that never grow. A good example is an index on a serial number. You're never going to go back and insert rows on past serial numbers. They're always going to be added to new pages at the end of the index. So they never do index splits. You want to set the fill factor for 100. Now, if you have a table that changes a lot and the index field, and think about this as the index field changes a lot, you might want to use a fill factor of 50 or 60 or 70 to save a bit more space for growth. And when you create the index, it's adding the keyword fill factor 50 or fill factor 100 at the end. 90 is a default. It's in your on config file, so you don't have to do anything if you want 90. Now let's talk about a functional index. This is another type of index. It's a user-created index. And there can be all kinds of functional indexes. Some can be created in C. They can be created as part of a data blade package. If you get the spatial data blade, you'll get several R-tree functional indexes with it. Functional indexes can also be created in SPL, stored procedure language. And they can be very simple, as this example I have here, where I want to create an index where it uppercases all of the last names. Now, in order for this to work, you have to create a function called toUpper. And so here's my example. I have a function called toUpper. I'm creating it. It has to be non-variant. That means it can't have a varying return to be used as an index. And all it does is use the upper function built into Informix to return name in all uppercase. So now if I can test it by running a little test where I say select state name, upper, and if that works, now I can create an index. And the index is only going to be used if the where clause has this toUpper function to convert everything to uppercase. If you just type in uppercase without the toUpper, it's not going to know to use that index. But if you use the toUpper function to uppercase everything, this will be used. Another type of index is forest of trees index. And this is, to me, another form of partitioning an index. It's a B tree index, but instead of having one root node, you will have multiple root nodes. And therefore, there'll be less contention because every index read has to start at the root node. And that root node gets locked all the time. And if you have a very big table, this can spread things out quite a bit. Basically, it sets up multiple trees with multiple root pages. And so I liken it to a partitioned index. You say, well, I'm looking for fiscal year 10, go here. Fiscal year 11, go right here. Fiscal year 12, go right here. And then it just treats it as a regular B tree index. Now, another question that gets asked is, what's the best page size for an index? And this is where you really want to take advantage of the 16K page size, because the 16K page size means, one, you can put more index items on a page. There's less I/O. You'll have less levels. And you can create a separate buffer pool just for indexes if you only have indexes in your 16K page size. So I try and do that when I'm building a system. If we can, we'll put the big indexes. Small indexes, it doesn't matter. If a index is going to fit on one 2K page, don't put it in a 16K page. That's just wasting space. But your larger indexes that take up more than 16K definitely will improve on a 16K page, because now you can have the whole index on one page instead of having it on 4 2K pages, and you've just cut your I/O down from 4 to 1. And when you get bigger tables, that can be a huge benefit. Index partitioning. I'm going to refer you to a webcast I did last year on partitioning. look at the details on this. But you can partition indexes several ways. First best practice is always put your indexes in a separate DB space from the data. That at least means they can read the data and the index at the same time in parallel. So that's, to me, the first basic step. Always put your indexes in a separate DB space. Then, and my rule of thumb is if a table is greater than 2 gigs, then it will benefit from partitioning. If it's less than 2 gigs, don't worry about it. But you want to partition the index the same way the table was partitioned. So if you do it by expression, list, or interval, you want to partition it the same way. This enables when you detach a partition and the index matches a table, the index can get detached instead of having to be rebuilt. If you don't partition the index the same as the table, every time you do a detach operation, you have to rebuild all the indexes. Now, you can partition indexes using a different expression than the data, but I have yet to find a reason to do that. And if anybody has one, I'd love to hear about it. So I know this is hard to see. This is an example I gave last year in my presentation on partitioning. I'm going to make it full screen. I have a table. I'm partitioning by range on order date on an interval. And I then load a bunch of data. And then I create a unique index on order number, order date. All it has to do is that field that you partition the data has to be part of the index. And that way it will then partition this index in the same way the data is. And after I'm done, I can alter the table and add a primary key on order number since I've got that index there, and everything goes good. Now, this is rarely a problem now, but in version 7, indexes were attached to tables. And that means that indexes pages were mixed up with data pages in the same table space. In version 9, that changed, and everything now is detached. That's why when you run certain on-check commands, you'll see your indexes showing up as if they're separate tables because they now have their own table space. And that's much better. If you did migrate from version 7, you ought to just check to see if you have any attached indexes and drop and recreate them. Now, what's new in 14? I gave a talk about this a couple months ago. And there are 4 things I want to highlight that affect indexes. Number 1 is index rebuild. There are a number of cases where in earlier versions, and one example is a varchar length changing, where the index would have to be rebuilt. Now it doesn't. Anytime a column increases, you do an alter column to increase, the index does not need to be rebuilt. That's a cool feature. So it makes a lot of your column changes. Another key one is like going from serial to serial 8 or big serial. Makes a lot of your column changes much quicker that way in version 14. The second one is you can now rename system-generated indexes, and I think this is very cool. So you can rename an index that has a space in front of it to something with a real name. Now, when you do that, that makes it a separate standalone index. And now you can drop the constraint and the index will stay there. You can also rename the constraint. So you can rename the constraint to whatever you want it to be. So there's some really cool features in 14 that help index. This renaming indexes, I think, is the key one. And after you upgrade to 14, I'd really recommend you go through, look at all your system-generated indexes, and it takes an instant to do a rename, and it's done. And now your index has a separate real name. Now, how do you speed up creating indexes? A couple of things happen when you create an index. The big one is it has to do a sort of the data, and it has to sort the data, and that's going to take CPU threads, it's going to take memory, and it's going to take temporary space. So it's a good place to use PDQ priority if you can. Excuse me. And what you want to do is have enough temporary DB space, at least 3, so that if you use PDQ priority, it can do 3 sort threads. If you have more than 3, that's great. And then it can sort the data in parallel. And so if you have 3 DB spaces, basically your index builds will be 3 times faster than if you only had 1. There are also 2 parameters, psort nprox and psort db temp, that can be used to speed up indexes. And this is an environment file I use for building indexes. I set my PDQ priority to 100 because nothing else is on the system and I want to get this index built as fast as possible. I tell it to use 4 CPUs. Don't give it more than the number of CPUs you have. I'm telling it to use 4 CPUs for sorts. And I'm telling it to do the sorts instead of in a DB space on a file system. This only works when you have a very fast file system. So if you have like SSD drives someplace, setting this up to use the SSD drives can be very fast. I recently did a migration for a client, and it was interesting. Their data was on SSD drives, and we tried this, and it made no difference because the data was already on the very fastest SSD drives. So as people migrate to SSD drives, this option may not work. Now you do have to create the folders for this to work, or else it won't be able to sort the data and you'll get an error. Now, how do you maintain indexes? There's really not a lot to do. That's one of the great things about Informix. I teach a lot of DBA classes. I get a lot of Oracle DBAs coming in, and they always talk about having to rebuild indexes. You really don't. If you have to rebuild indexes, something is wrong. And the number one thing I've seen is people are using kill 9 on a user or on the server. And that may leave your data, and particularly your indexes, in a very inconsistent state. It's much more efficient just to drop and recreate the index, to rebuild the index. And that's something I've had systems that have run for 5 or 6 years without ever doing that. Actually, more than that. I've had systems that have been upgraded without dropping and rebuilding indexes. It's not a requirement, and it's actually not a lot you really need to do. Now, one key, though, that you should pay attention to is the B tree scanner. The BTS scanner, this is a thread that runs in the background. So if you come over here and you do an onstat -GATH to look at all your active threads, you should see something called BTS scanner. Whoops, there it is, BTS scanner. And it's running in the background, and it wakes up and goes to sleep and wakes up and goes to sleep. And what it does is it goes out and says, do I have any indexes that need to be cleaned? And there are a number of parameters. The first one, and I think the only one I really think I mess with, is the number. And that's how many threads to run. Uh, the default is 1. If you've done a big purge, it may be helpful to run extra threads for a while until it's had a chance to run in the background and clean up your list. And I'll show you how to do that in a minute. So this is the number of threads to run. The threshold is the minimum number of deleted keys for it to prioritize cleaning. 5,000, that means you've got to delete 5,000 rows for it to make it a priority to clean. It'll still clean it. It's just going to be run. And range size, I leave that at the default -1. Alice is there's a fancy name for Alice, and I always forget what it is. 6 is the default, and it basically says, here's how much memory to use for cleaning. And then the compression level for partially used pages, the default is medium. Now, you can, without changing your on config, you can use on mode -C start 1 to start another B tree scanner. So then you could do on mode -C stop 1 to stop that scanner. Now don't stop one if you only have one, because that means you'll have no scanners running, and that can be a real problem. But you can, after a purge, maybe do on mode -C and say start 3 or start 4 and let them run for a day. And then at the end of the day, stop them. And that way you can maintain your B trees. And they run in the background. They are low priority. So they go through and clean up things in the background. Now, to monitor this, there's an onstat command called onstat -C, which basically shows you the information about the B tree scanners. The only one I really look at is the onstat -C by itself and the onstat -C hot. This tells you how many index keys need to be cleaned. So if I come here and I do onstat -C, you can see I'm running one scanner, and it's hardly taken any time because I haven't really done much work on this system. It does have seen that there are a lot of deleted items because earlier I did drop and recreate data. So let's go back here and I'll do the on mode -C start 1. So now I've started another scanner, and now I have 2 scanners. And it's building a hot list for it to go work on. It'll take a couple minutes for it to get all the calculations of what it needs to do. And so these 2 scanners will divide up the work and go through. Now there's not really much to do, so I'm going to go ahead and stop it. And now I'm back to 1. So this is something to, particularly after you do a purge, run it, and then when you see your hot list, and you just do onstat -D hot, and I'm going to type more. This tells me, my current list has only got 12 items on it, not very big. When you see this getting big is when you need to worry. I don't have much cleanup work to do. So on stat minus C hot, and this tells you the index partitions that need to be cleaned up. Now, there are also on-check options to check indexes. And there's a lowercase I and a capital I. And the lowercase I just checks the index. The capital I checks the row ID and the database. I actually think it's a waste to run just on check minus lowercase I or capital I by itself. I prefer to run on check minus C, capital D, capital I. This will check both the data and the index. So if you're worried about your indexes, run this on the table and it will check all the indexes. You can also do number index name and it will just check that one index if you think there's a problem with an index. Let's say someone is reporting errors with an index. You can run this to see if there's an error. Now, my rule of thumb is when OnCheck finds a error, it will prompt you, do you want me to fix this? So you need to either put a minus N at the end of this so it doesn't fix it by default. It doesn't sit there and prompt you. Because I've always found it's faster to drop and recreate the index using PDQ than have OnCheck fix the index. OnCheck is going to do the index serially. So it will only be one thread chugging along in the background. It'll lock the index and it might take a long time. You're much better dropping the index, fixing it, recreating it, and that will fix the problem. Now, a really nice new option to OnCheck that I'm hoping means there's going to be more is how do you know when an index was last used? There's an option to OnCheck minus PT that is in version 12, the later versions of 12, and it tells you the last time there was a lookup or scan on an index. And let me come back over here and which one is that to run? Okay, so I just ran OnCheck minus PT on the bills table, and it's telling me I've got a very fragmented table with a bunch of extents. And then it comes here and tells me, here's the information about the index. And it says, hey, this index was last used today at 11:58. So it can give you an idea of if your indexes are being used. Now, if it's never been used, it will have a blank here or say no data. So I find this a very helpful new option. Again, this is in 14 and the later versions of 12. Now, how do you monitor index usage? I had a script that I shared with people in the past, which had a problem with duplicate index names because it did the join between the profile in the SysMaster database based on the index name. So I've rewritten this script, and this is brand new, and this is my takeaway from today's presentation, and you guys get to see it first. And now I'm using the partition number, which is unique to every index. This also handles partitioned indexes. Let's say you have an index that's partitioned into 12 partitions. You will see 12 records now, one for each partition, telling you the IO for that partition. And what you want to do is compare reads to writes. And I have something I call the ratio, and that's the ratio of reads to writes. The higher that ratio is, the better it is. Here's a script, and here's a look at the ratios. So here I've got an index on state. It's had 15 reads and 11 writes. Now, to write the index, it has to read it. So in reality, that index has barely been used. It's only been used 3 times in queries. It's poor index usage. Now, the problem with this index is I need it because it's the primary key on the state table, so I can't get rid of it. But at least this tells me that this index is not used. Where this script is really helpful is when you have a table with 5 indexes and you're trying to figure out if you really need all 5 of those indexes. This is an example of a great index. It's been used 677 times for every write. That's an excellent percentage. Here's an example of a good index. It's been used 46 times for every write. Now, part of that is I've been doing a lot of inserts and updates and deletes on this table, so it does get a lot of I/O. But you want to see more reads to more writes to tell that an index is good. And let me just give you an example here of this. If I go into DB Access, and I'm going to pick, I'll pick my other database here I haven't used. And the script is going to be called indexusage2.sql. And I'll have that available for download at the end when the slides are up. So I'm going to run it, and it tells me, okay, here's a warehouse table. It's had 64 reads, 11 writes. Not very good. This has had a few more reads, a few more writes. Not very good. This basically is a database I just loaded and I haven't done anything with it. And so this gives you an idea. 5 is about the number of reads to writes when you just load data. I literally, all I did was I did a DB import into this database. And so I'm seeing 5 or 6 as a ratio. That tells me that the indexes have not been used for anything except being created. So let's go pick another database. And I'm going to pick benchmark 2 and run this. And now you can see, okay, the state table has a huge ratio on this index. Here's my upper function. I haven't used it. I created it. I haven't really used it. So it's got a ratio of 1. My customer primary key index has been used 46 times. That's not that great. My product index has a ratio of 6. That's not that great. And so on and so forth. You will see some where it has blank because this depends on sys profile, which only has records if the data has been used. So here's a table and an index that's just not been used since the system was last started. Now, every time you shut down the system, restart it, all these stats get zeroed out. So I went over and if you take a minute, find the chat button. I will take questions. Good question. Best way to kill a user. On mode -Z and the session ID of the user. When we do the class, one of the things I want people to walk away from in that class is how to kill a user, and it's on mode -Z with the session ID of that user. And I'll give you an example of it, just because you asked. So on stat -G SQL, let's find out the user. I'm in benchmark 2 database, so that's my session ID. I'm the user Informix. You have to be the user Informix to do that. I'm going to do on mode -Z 1513. Boom. I've just killed that user. Their session ID is gone. Now, I'm still sitting here at the screen, but what's been happened is I've been disconnected from the database. Now you can do kill -9 to kill my DB access if you want to. But do the on mode -Z first? That was an excellent question. While you're thinking of questions, let me go through just a couple of other things I want to point out. Coming up in September is, I think, the most exciting event of the year, the Informix World User Conference. It's in California. There's tons of information there. We're going to be there. We're a sponsor of it. Come see us. We'll have some of you may remember the notebooks we had in the past. We have some new notebooks that we'll be giving out. We have a quick reference guide for version 14 that we'll be giving out. Plus, we'll be doing a number of sessions. And Tom and Mike and Art and myself will all be doing sessions over the course of the data. So the other thing I want to point out is I have 2 more webcasts coming up. We're going to take a break in September, and then in October, I'll do one on looking at the SQL query explain plan, and then in December, one on update stats. We try and do one maybe every month, every other month. Tom, Mike, Art, and myself all work together on these, and so keep an eye out on our webpage. We'll have a bunch of new stuff for next year. The other thing I want to mention is training. I think we're about the only organization that does Informix training now. We had 2 great public classes. In addition to these public classes, we take, and I've taught more private classes. If you have 4 people, contact us about a private class, because it's cheaper to do a private class for 4 people than to send those 4 to one of our public classes. That being said, we have a class coming up October 7th. We've already got registrations in for that. The course is definitely on. We have never canceled a course in the last, I don't know, 5-10 years. I'll teach a course if one person's registered. And this is the training room. We have room for 8 people, 4 people in our classroom, and we can have 4 people online. We can actually have all 8 people online. I don't like the classes where everybody's online, because I'm sitting here in the classroom talking to the monitor and everybody else hears me. But, we use WebEx, you SSH into our servers. So all you need is a web browser to access WebEx and SSH, like PuTTY, to get to our servers. And just a quick moment on, besides training and webcast, we also do performance tuning. We do 24/7 DBA monitoring for a number of clients. We do consulting. We've done a lot of migrations. I'm working on 2 migrations right now. A lot of people are upgrading, some to 14, some to 12. Be glad to help you with that. And so let me take a look at the chat and just see if I can catch up on questions. So indexing blob and clob columns, not a good idea unless you write your own data blade for that. If you have a data blade, that is what you want to use to index it. So you need to think about, and particularly if you have blob or clobs, you need to think about it. Now, there is a text data blade that you can get, and that does have indexing for blobs and clobs. But again, that's adding a data blade. Now, changing the data type from varchar to big int, yes, because that is not necessarily going to be a change from, if it's varchar 30 to big int, you're going from 30 bytes to 8 bytes. You would have to rebuild the index. That's a good question. The only time you don't have to rebuild the index is when you go from a smaller field to a bigger field. How do you know how many levels? That's a really excellent question. How do you know how many levels of an index do you have? And let me come back here. I'm going to run my onCheck minus PE. And where is it? This will tell me. Here in the onCheck minus PE, it will tell you how many levels you have. That's data. I'm looking at the wrong thing. So this is the table, and I'm looking at the index. And one of these will tell you, here it is. This tells you how many levels you have. And on check minus, let's just cat that and I'll show you what it is. Yeah, on check minus PT, database, table, number, index. I'm way over, but I'm going to try and is it good to run update stats faster with or without indexing? So good question there. In the later versions, when you build an index, it actually does update stats high as you build the index. So I think you need to run update stats with indexes. That will make sure the index data is there. I would not drop indexes to run update stats. But every time you build an index, it does in the later versions of Informix run update stats high on that column in the index. Another question, how long will it take and how much space is used by auto indexing? That will depend on how big the column is that it's indexing and again, how long it is. Now the optimizer has decided it's faster to do that than to do a sequential scan. So you would assume that it's going to be faster for the auto indexing than doing a sequential scan. And most of the time, the optimizer is right on things like that. Yes, the presentation will be available along with the replay. And yes, you can rebuild all indexes online. Awesome. Good questions, everyone. Well, this is fun. You know, it's a lot more fun doing these presentations. This is one of the biggest ones we've done. We had something like 85 people registered for this today. And a lot of good questions there. I really appreciate that. Thank you guys all for spending the afternoon with me. And I hope to see you when we talk about SQ Explain. And we'll do that. So thank you all, everybody. I really appreciate it.